basically what I'm pretty sure is happening is in the lectures, everyone's still going over beam design, right? Is that right? Flexure, like the T-beams, that kind of thing. If you saw in the concrete group chat, I've dropped in a week 6 yap. So that was a bit of a long session that was on Discord. That's like a real like step-by-step thorough worked question. This time we're gonna, because we've only got an hour, a little less than an hour now, we're gonna go back to the previous format, like week 5 and 4, where it's, you know, I'll just like go through the theory, really get those down. If we have time, I'll try to go through some like worked example stuff, but more or less will be theory related. So a couple of you guys have done steels, yeah? Do you prefer steel or concrete? Steel design or concrete design?
Maybe steels, I don't know. They do the same.
What I'll say is like concrete in week 5 is very much like you have to derive everything as if it's like solid mechanics, you know what I mean? Steels, you follow this really long like, you know, chain of formulas, right? And that's what this week will feel like. It'll feel a bit more like steels, right? You just plug and play, figure out where the formulas and stuff come from. It's like on like a Windows computer. It's like folders inside folders. You just keep digging. That's what this topic will feel like. So doing shear design, which is like a rather, and it's kind of like a difficult concept to understand. I don't fully understand shear, to be honest with you, but I will tell you from what I do understand. So like hopefully like a more practical point of view, right? So yeah. So in terms of shear, we're talking about shear. We're talking about the shear forces. You might remember like shear force diagrams from 1300, and just the fact that we have this, which is like the cross section of a beam that we've cut, right? So that's called our plane, like, and basically anything that's tangential to that plane, any forces, we call shear forces, shear stresses, that kind of stuff, right? So that's the kind of actions, external forces that we're going to be analyzing, right? So this is caused by, you know, point loads,
Henry,
distributed loads.
are you meant to be like...
Oh. Thank you. Not bad. Yeah. You didn't miss out on much, because literally this is the first thing, right? But yeah, thank you. So yeah, that's like your cross section, if you slice the beam in half, right? And then, yeah, these tangential forces to that plane, that's shear forces or shear stresses, right? Yeah. So this is called direct shear, what you can see here, right? But in practice and particularly for concrete, right? Beams fail in a slightly different way to this. Direct shear failure is quite rare because it usually fails in diagonal tension failure, right? Which I'll show you in a second. Because concrete is weakest in tension, right? So in reality, shear failure / cracking in concrete usually happens diagonally first. So if we look at a beam, right, actually, I might just do this from scratch. Sorry, I like to rub things out if I remember to first, so that there's like less to look at on a screen. So this is, you know, a beam column joint, right, rigid joint. And when you have all your like distributed loads and stuff acting over it, let's just say, you're gonna find flexural cracks developing in the middle. Yeah, Farhan?
So we're pretty much just looking at the side, right?
Yep, elevation view, yeah. So you can overlap like a bending moment diagram like this. And the max bending moment, right, it's like that, right? So these are called flexural cracks. It's kind of what we've been talking about and designing for in like the last few weeks, yeah. Next, well, like for this week, I guess, we want to be focusing on designing against shear cracks, right? Which look like this. So they can develop on like these sides of the beam, right? So these are due to a shear force diagram, right? Like the effects of a shear force diagram. Just have a think about it for a second. What will the shear force diagram generally look like for a beam, you know, that's experiencing uniformly distributed loads, like self-weight and stuff? Linear? Yeah. It's like triangles, yeah? Yeah, so if I overlap it, like this, it looks something like this, right? So do you see how the peak shear is like here and here, right? So why do you reckon, you know, the shear cracks develop here? Here and here, more or less, in this kind of structure. Anyone want to give this a crack? Yeah, Ken.
Is it because of the supporting beams?
Very good. It's because it's rigidly connected, right? It's rigidly connected, and the columns are going to be able to like help withstand a bit of that shear, bit of the shear forces, right? So actually, we call this DO, right? Which is the distance to the critical shear from the support, right? So it's always from the edge of a support, right? This number in AS 3600, so this is like the Australian method that they determine that this distance. DO is the same DO as we use for the depth to the outer steel, right? So from the compressive edge to the outermost layer of tensile steel. So, you know, sometimes you can have two layers of tensile steel like this, right? It's always to that outer layer, right? Okay, so these are called shear cracks. And sometimes we get this like combined effect, right? I'm so sorry. This is gonna take like a minute. Just feel free to chat. I have to pull up my notes on my phone. Okay, sorry, I just wanted to make sure I was drawing it correctly. So shear cracks look a little bit more like this. They're a little bit more uwu, Janice. But the flexural shear cracks look a bit more like this. Right? These are called flexural shear cracks. Why do you reckon they're called flexural shear cracks?
Combination of both.
Yep, it's combined action. If you overlap like the bending moment diagram and shear force diagram, you can kind of see that in these regions, this is where there's kind of a bit of both, like the bending moment and shear force that's acting on it, right? Okay, so here's like the overall equation we're rolling with for shear design. Yeah, I might turn off the slide. So, yeah, left-hand side will still be from a shear force diagram, but we're not taking the max shear anymore, you know what I mean? We're taking that shear at that location, right, which is DO away from the edge of the column. Oh, sorry, from the support, right? And then this value phi, which we've previously had to calculate through ductility, right? You know, it's like 0.85 in flexure for a ductile section, 0.65 for a brittle section. This time it's easy for shear, it's always 0.75. So this isn't a hard part of the calc anymore. Well, I mean, it never really was, but it has less steps. But this VU is deceptively, you know, it's deceptively difficult to actually work out, okay? So, what should I talk about first? Okay, so you can break up that right-hand side into essentially three further components, right? So this component is VUC. So V, by the way, is, you know, how we denote shear force with V. So that's shear. U is ultimate capacity. So whenever you see a U, you know we're talking about the ultimate limit state, strength design. Yeah, basically where it's fucked beyond belief. And then C refers to the concrete portion of the strength. So you can imagine, because we have a combined material, right? We have, you know, concrete and reinforcement. The strength of this entire section you can simply just add together these two components, right? Like, the strength contributed by the concrete plus the strength contributed by the steel. So that's what we're doing. So VUC is due to the concrete portion, right? It's called the concrete's capacity, right? VUS is the stirrup capacity or the steel capacity, right? So remember, stirrup is one of those ways of referring to one of those shear bars, or like the shear bars in general, right? They're also called fitments, they're also called ligatures, like fucking 5 names for them, right? And then there's also the pre-stress capacity. You'll see this in the AS3600, but Taiwan won't refer to this because it's not in the course. This is in pre-stress concrete, right? Yeah.
Do we still have to include it in our calculations though?
No. I don't know why I included it, to be honest. Just scratched it up straight away. So don't worry about it. But it does exist if you're interested in whatever. Say you get a job in a structural engineering firm, whatever. You'll see it and you'll be like, what the fuck is this? I'm just telling you what it is, right? But basically the concrete capacity can be derived further, split up into 3 additional components, right? It's called the dowel action, which is D, the aggregate interlock, which is A, and then the concrete itself, the shear strength contributed by the concrete material itself. So let me just briefly explain what these are. Dowel action is referring to the axial bar, right, as a dowel. And dowel, I don't know what the actual definition of dowel is, but okay, I've been watching Japanese carpentry videos, right? And basically they have dowel connections. It kind of interlocks the timber using only timber, so they don't need to use screws and shit. That's just Japanese joinery, that kind of stuff. So that's dowel is kind of rod thing that interlocks.
It's like a wooden cylinder, though.
Yeah, it's like a wooden cylinder. That's for timber specifically. Dowel referring in this context is referring to the steel as a cylinder contributing to interlocking the concrete. Yeah. And then the aggregate interlock is also the interlock. So again, shear action. Shear action is like this, right? You're stopping the concrete from slipping along its slip plane or diagonally, like that. The aggregate interlock is that friction from the aggregate scraping against itself, and that'll contribute to the strength of that concrete, right? So it looks kind of like this. They've loosely drawn this. Again, this is all derivations, by the way. These aren't things that you need to draw out in your fucking exam and stuff. Dowel action is from like this. So they've referred to the tensile bars here. And yeah, that dowel, interlocking the concrete, contributes to the strength. The aggregate interlock, and then the concrete. I don't know, these arrows are kind of arbitrary. I'm pretty sure this is from Daniel O'Shea's pre-stress slides, because I thought it helped visualize it a little bit better. But yeah, you just need to know that all the concrete strength, which is VUC, comes from these 3 components, right? And then yeah, they have more diagrams to explain that. Yeah. Okay, so basically now we're going to talk about the stirrups, right? So there's stirrups referring to the steel, the shear steel, right? And here's where this comes from, and how they kind of derive the functions. So trusses, right? Trusses obviously work a little bit differently to beams, but have you guys seen what the steel cage stuff looks like? I might draw it out. So there's the axial compressive bars, axial tensile bars for a simply supported beam. You kind of have this cage that locks around like this, right? Yeah. So basically, the tensile steel, these that I'm drawing here, these are the stirrups, right? We basically have formed a cage where it behaves similarly to a truss, right? So when we're looking at it side on, those vertical steel members, they're taking on tension, right? And then, so just have a look at this beam, right? Do you remember how we've talked about that top axial layer being in compression for a simply supported beam. And we've talked about this bottom layer being in tension, right? So in our truss analogy, these axial bars still it's still consistent with these rolls, you know what I mean? So like at the bottom, this steel is taking on tension, right? The bottom layer is in tension. And in a simply supported truss, you're going to find that the bottom layer is also going to be in tension when the truss is like bending like a simply supported element, right? But what we've said here is the concrete takes on the compression, right? So the concrete will act diagonally, okay, like this, and and that top chord is steel in compression as well. But that concrete acting diagonally, just like it's a bit of a weird thing to think about. I don't know how to explain this properly. Basically, yeah. Anyway, we're gonna keep going, and then maybe it'll make sense, right? So with our stirrup, so how we calculate the capacity of the stirrup. So again, we're talking about V US, right? So that's steel component. There's a few random like Greek letters and shit that you're gonna have to get familiar with here, right? And what they all mean, because they're quite abstractive concepts, right? Firstly, spacing. So spacing is probably the most intuitive. You know, do you reckon that a bigger spacing will result in higher strength or lower strength? This is steel. Yeah. And vice versa as well. So if you make it tighter, right, that's going to be a good thing for the strength, right? So the spacing is very important for the overall strength of this beam. But because we only design section by section, we're going to need to have this kind of ratio for the strength per spacing. Do you know what I mean? Based on how far away it's spaced apart. dV, you'll find out later. dV means the internal moment lever arm. Okay, so it's basically a function of the effective depth. So it's to do with the lever arm in like your moment equation for your tensile bars, right? Yeah. Anyway, just consider it as some distance, right? That's vertical. Okay, here's where it gets cooked. So, theta V is the inclination of the compression strut. So here's where it comes together. The compression strut isn't like an actual thing. It's the angle which the concrete will take on the shear forces. Do you remember how we talked about the shear causing like these cracks and going this way? Right, kind of like diagonally. So that is to do with that value, theta V. It's the angle that the concrete will fail, right, and crack and stuff like that. So that's what we call the angle of the compression strut, right? Following? Okay, and then X, this is X is kind of like basically X is just the resultant distance, right? Because if we know the angle that the concrete is going to crack in, and we know that lever arm or whatever, we can find out that projection distance X, right?
Rise over run.
Yeah, it's like rise over run stuff. Yeah, exactly. And then that angle there is theta V, right? So we basically know a bunch of other stuff other than V, and then that's what we solve for, essentially, right? That's called a horizontal projection. But yeah, you're right, like rise over run, that kind of stuff, right? So these are all derivations so far, right? But I just want you to know when you see X on your page, you know what they're referring to. This is important because we need to know this ratio, X to S. So this is the ratio that I'm talking about in terms of when we're designing for the strength of the steel stirrup. It's a ratio of this horizontal projection over the spacing, right? Which means that as you increase the spacing, you'll get weaker. As you decrease the spacing, you'll get stronger, right? we all good? That kind of concept? Right, so it's because it's kind of like if we're just designing for one section like this, you know, how do we get that as a function of spacing? So this is the way that they've derived it and found a way to get it as a function of spacing. Okay. ASV, you'll find soon, means the area of shear of the shear bars, right? Like the stirrup area, essentially, right? And then FSY.F means the yield strength of steel when it's used as a fitment. F means fitment, which means stirrup, which means ligature, which means shear bar. So that F isn't flexure, it's as a fitment. Trust me, I've gone down a rabbit hole of looking through like fucking AS30, 3600 and like the definitions and stuff. So basically both of these are to do with the stirrups, right? And this is to do with the stirrups, and then that's how we get this big formula. They get this derivation, chuck it into here, and that's how we get it, right? Just a little reminder as well that cot theta v is 1 over tan theta v. So whenever you see that, that's actually what you punch in your calculator. Yeah. Okay. Oh, does anyone have questions first before I move on? Okay. All right. So now I'm going to go through the step by step of what we do. Yeah. You know what? This probably helps if I. All right, go on Smoko for like a minute. I'm gonna rub out some stuff, and then I'll test you.
I'm running a new. Maybe get
Get off the double.
My grants just go fire. To practice your handshakes.
Gotta keep it tight, you know?
Yeah.
Keep it tight.
You yapping? What's going on?
Yeah, hold on, mate. Hold on.
Hey.
I want Smoko.
No. This is just a randomized, testing. Yeah, I'm just reviewing your workshop, and it's not looking very good for you, so.
Fuck off, James. Okay. All right. So we're back. All right. All right, guys. Smoko is over. Okay. So let's keep it simple. What do we have here?
Just repeated like on a beam.
Yep. Simple supported beam, UDL. Yep, that kind of stuff, right? I've also specified here that it's a beam column joint. So that means that it has those properties we were talking about before, like that. Do you remember? Yep. So it has a little bit of rigidity. We're going to do shear design on it, right? For shear design, we also want to find M star, so it's the bending moments and stuff like that. But let's worry about the shear component first, because that's the thing we have to worry about. I'm going to teach you about this method. So we're analyzing just the left-hand side, yeah. So we're talking about this side, and then that's like all that shit with the VU, right? Let's talk about that later, right? Right now we're just focusing on the left-hand side, the external forces, right? Okay, so we're told, let's just say that Q is 170, right? So the live loading, it follows this uniformly distributed load pattern. And then G, the dead load, is 121, including self-weight, like that, right? What are our load combinations? Does anyone remember?
1.2 G plus 1.5 Q.
Yep. 1.2 G, 1.5 Q, what's the other one?
1.35 Q?
1.35 G,
Or
yeah.
G, okay.
But yeah, so in flexure, when we're doing flexural design, every now and then the dead load comes, right? But usually it's this one with the live loading included, and the live loading is like significant at all, right? But for shear force, we have to consider both, and we have to draw the shear force. Not the shear force. Yeah, we do have to draw the shear force diagram for both. And it gets even more cooked. We have to, even if we have a simply supported beam with a uniformly distributed load over the entire thing, when we're considering the load combo of 1.5 Q included, we only place it over half the beam because it will induce a greater shear force in the middle. And then we take the worst case scenario of all of them, kind of like merge the points together, and that's called our shear force envelope. So I'll show you what I mean. So the first thing is I've calculated just the overall load combo. We know that this load combo governs, right? Because Q is significant, right? So I've called this WU. WU is 400 kilonewtons, right? But we're gonna break this up a little further. We're gonna call this, actually you tell me, which part is Q and which part is G?
Front part is Q, left part is G.
We're gonna call this WQ, W star Q. We're gonna call this W star G, okay? Yeah? And so whatever that equals, I'm pretty sure, calculate it. That equals 145, and then GQ is equal to 255, right? Okay. Now we're gonna move on. So shear force envelope, I'll show you below. For moments, simply use this number, plug it into this formula, and for X, you want to put in DO. DO being that critical distance from the support. That one's not bad. That one, you're just chucking a formula for a simply supported case. The hard thing here is drawing the shear force envelope. Right? Okay, so you need to basically calculate two scenarios. Here I've labeled them 1 and 2. The first scenario is max shear force at the face of the support. So this is your standard, you apply WU, or like the worst case loading condition, to the entire beam, right? So this is called WU is 400, right? And when we calculate it, the shear force diagram will look like this, right? So the peak will be here and here are the supports, right? So you can calculate that simply, if you like, using this support value is WL on 2. W star U L on 2 is equal to that, right? But okay, actually, sorry, I lied slightly earlier. We're only considering this load combo, so we're not going to do anything with 1.35G. But even with this load combo, we have to take the worst case scenario within this load combo, right? So in order to get, because you see this shear force diagram here, in the middle, right, we have the shear force of 0, which that might not truly represent what the worst case shear force is. To represent what the worst case shear force is, we have to just, we stack the live load only on the left or the right. You can calculate it either way, but it will give you similar numbers basically, right? So WL is 255, right? So 255 comes from this, right? And then sorry, I've called them something slightly different in my notes. The dead load I've just called WD as like D for dead, and then WL is live. Yeah.
That blue UDL, is that 3.5 meters?
Yeah, half a span. That's the way you get the worst case shear force in the middle.
So it's out to the right or something?
Yeah.
It doesn't matter which one.
Yeah. So just if we keep going for a bit, you'll see how it plays into effect. I'll answer your question in a second, basically. WD was 145, right? And then when you calculate it using, so at this point you can't use a formula. You have to hand calc this using your basic 100 abilities, right? and then you'll get that this support on the left is 1177. You get this support on the right is 1731, right? Okay. So yeah, basically, yeah, Farhan, to answer your question, if you stack it on the left, it'll look like this, right? Wait, Farhan. Wait, sorry. So if you stack it on the left, sorry. Basically, if you stack it on the left, it looks like this, right? But if we instead stacked it on the right, like that, it'll look like this.
Would you have to do both cases?
Yeah, but it's actually one of those things where it implies both ways, even if you do it once, I guess.
Is it like symmetrical?
Yep. Yeah. So it's like this, right? Do you see how, like, because of the symmetry, it flips around?
Yeah.
Yeah. So it doesn't matter which way you do, but all we care about is this number in the middle, right? Because these will always be smaller than when we stack the shear force on the entire thing, right? So that's why we're doing the max shear force in the midspan. And then the shear force envelope looks like that, right? You see these numbers? So the shear force in the middle, you just have it both the positive version and the negative version. Yep. And then we can actually create a equation from it. You have to derive this using your linear algebra a little bit, right? But it's just like y equals mx plus b. And the distance we care about is dO, right? dO being the depth to the outer steel, right? Like that. And yeah, and then you can find what V star is. It takes a while, but yeah, that's it. Okay, so okay, there's a lot of steps coming up. Wait, Lockie, do you want to talk about? Because I think I know what you want to talk about. Oh, do you talk about the bet?
No, you can finish.
Okay. Okay, basically, that was step one, it's left-hand side. Okay, next step, we're going to have to check for something called web crushing failure. This is like a premature failure mode, similar to in like steels, if something buckles before it's supposed to fail in flexion normally, right? Or if something, say there's bolts running through your truss member and it's being pulled apart, right? Fast fracture occurs earlier than the normal failure, which is our yield failure, right? So this is like just another type of check. It's a web crushing failure check. And it's very like plug and play with the formulas. But because we do this check first, we just happen to be calculating a lot of these values, which we're going to be using throughout all of our shear design, right? So these important values are shear width, which is BV, internal lever arm, which I've talked about a little bit in like the derivation, but that's to do with the lever arm of the steel and yeah. And then the inclination of the compressive strut of the concrete, again, that's essentially like the concrete cracking angle, right? That's like the most simple way you can put it. And yeah, so this is plug and play. So first, I tell you the order you calculate it because some of these formulas are dependent. I believe, in particular, theta V is dependent on 1 and 2. So 3 is dependent on 1 and 2. So we do 1 and 2 first, right? 1 is the easiest to do. So again, for non-pre-stressed concrete, which is everything in this course, we do BV is equal to the web width, right? So if we have T-beam, that's the web width, right? Okay, DV, you take the max of two numbers. The first number is the overall depth, right? So that one's not too bad to understand. That's the overall depth, right? And then the effective depth is this, right? The depth to the centroid of the tensile steel layer. So, question, is this the same as DO?
No. DO is the furthest one, right?
Yeah.
The furthest layer.
So, where would D be if I had two layers?
In between.
Very good. So they're different if there's two layers. If there's one layer, they're essentially the same thing. But yes, they're not the same, so don't get them mixed up. Yeah. Okay, and you just multiply it by like some reduction factor, which is listed here, and you take the max of those two things. Okay, all good. Next, we do theta v. So theta v, here's the important part. In your finals, and in my finals, it's only ever just been taken in the simplified method, I believe. 36. I'm pretty sure. I'll double check. But I'm pretty sure it's only ever just 36. Because this part takes a while, basically, right? And there's more stuff they want to test you on. But in all the workshops and stuff, they want you to do it the other way. This way only works for non-pre-stressed concrete. So if you do go on to do pre-stressed concrete as an elective, you have to learn the other way. There's no way around it, right? So this is like the detailed method, right? This is already shortened. So if you look in the AS3600, this is like a really long formula. It's longer than this. If you're dealing with pre-stressed concrete, this is like way more components. There's another component at the top and two more components at the bottom, right? But this is already the simplified version for reinforced concrete, right? So it's called the longitudinal strength at the mid-depth of the section, right? So if we have a T-beam, right, we're talking about the mid-depth, that's D over 2. That's not the neutral axis, right? So longitudinal strain, if we look at it side-on, right? So that's the T-beam, where that's the flange, right? We're talking about this, how much it's strained away from where it's supposed to be, right, at that mid-depth. Okay. But this is why we had to calculate the left-hand side first. The left-hand side being like, V star is less than this shit, right? We calculate the external forces first because this formula is dependent on V star. And not only is it dependent on V star, it's dependent on M star. So that's why in shear design, we also calculate for bending moment diagram. Right. And this number can't be greater than 0.003. This is like an additional fact. And yeah, other than that, that's fine. These are all numbers that you will have access to, and then this one we've calculated. That's what I mean by it's a dependent formula. So rather 3 depends on 2. Okay. So this isn't, we didn't actually calculate theta v. We calculated epsilon x. Now to calculate theta v, we get this formula I'm going to call. And then whatever you get from this formula, it's going to be in degrees, right? So even though this is a unitless value, because it's strain, we're going to get the answer in degrees. Right, so I usually call this theta v degrees. You don't need to convert to radians and shit, basically. Right? This isn't fucking maths or like first year physics. Concreters just want things in degrees and like normal units, you know what I mean? Okay. And basically, we do a quick check to make sure that that left-hand side, the external shear forces, is less than our web crushing failure, right? So if our web crushing failure fails first, we have to reassess from that point. But in all of your exams and questions, it's always gonna pass this check basically. This number will be really high basically. Okay, next up is to find the minimum shear area for the steel per spacing, right? Minimum being because, anyway, whatever. We just find this first, right? This is the steps. This is a formula that they've derived, right? And it's a function of, sorry, I read this wrong in my notes. That should be FSY.F, right? So that's the yield of the steel if it's used as a fitment. So that .F, it's not the same as, do you remember FCT.F?
When does the class finish?
little less than 10 minutes. Yeah. So this is due to this is tensile flexural strength, right? But here we're talking about steel used as a fitment, right? So this is really important because even if your steel has 500 MPa for its yield strength, sometimes you see questions where the fitment strength is 500 MPa, but sometimes you see it as 250 or something. That's like a twofold difference. So you have to really check what the question tells you for when it's used as a fitment. This is the exact same like N12 bar, for example. When it's used as a stirrup, it can have different properties. Okay. Does anyone have any questions to do with that specifically? Okay. Okay, so now we're done with those preliminary checks. Now we have to calculate the concrete strength, right? And then later we're going to calculate the stirrup strength. So aggregate interlock factor is new. We've already calculated BV, DV, and we're given F-C, right? So BV and DV we calculated a little earlier. KV, the aggregate interlock factor, it's a formula that depends on whether your shear area is per spacing is greater than that value that we calculated earlier, which is the minimum, right? And we always start by assuming that it is greater than the minimum, and if it's not, we have to try the other method. So if it is greater, right, we have a simple formula, right? And we've already calculated epsilon x, so that's all good. If it's not, right, and you can check this later, right? You have to go back and check if it's less than the minimum. Then basically some of the aggregate will take on the, the aggregate will contribute a little bit, right? So if the steel isn't contributing enough, the aggregate will take over, basically, right? And this is called an aggregate size factor, and it has this formula, basically. Usually the max aggregate size is given, otherwise you assume it's 20 mil, right? This is the maximum rock that can be in your concrete mix, right? Okay, basically now we're checking whether the concrete itself can take on our shear strength, right? Because if the concrete itself can take on our shear strength, and you'll find that when we do slab design, right? And slab design is, you have a fucking slab that looks like this, it's 1000 mil. Sometimes the concrete is enough to take on the shear itself, and you'll find that for slabs we don't actually really have stirrups, right? But for beams, usually it needs shear assistance. It needs these kind of shear bars to help out as well, right? And so we have to add stirrups, right? And the stirrup area per spacing has to be greater than this formula, right? So this is already the derived formula. It's from the combination of the left-hand side equation and just breaking down this further to like VUC plus VUS, and then like they fucking rearranged it and stuff like that, right? So this is just like the expanded out formula, right? This we've calculated, this we've calculated, this was 0.75. This we're given, this we're given, this we've already calculated. It's just a bunch of plug and play, right? Okay. The actual shear bar area, I want to talk about this before I finish up. The shear bar area itself, right? We have to consider all of the legs, right? So this is called a double-legged, let's say it's an N10, right? This is a double-legged N10. So whatever you have from your table, right? Did I say N10? Yeah. You have to times it by 2, right? So it doesn't count as one N10, it counts as 2 N10s, right?
Wait, is it because it's double-legged?
Yeah. So this is double-legged. It's because we consider the shear that crosses over this area kind of like sideways, right? Okay, I've got a question for you. What would this area be? Area of N10 times what? Yep. So 1, 2, 3. That's called a double-legged N10 and a single-legged N10. Single leg being just this hooks on and it has one leg. What about this one? 4 N10. This is called 2 double-legged N10s. Right? Makes sense though. This one's not too bad, but the terminology you gotta get used to. Okay. Basically, we should set the spacing. Oh, sorry. You have to choose. Okay, so you're basically gonna find what. Okay, just follow Clary's working. Basically, you're gonna find like some area, some trial area, and some spacing that hopefully lands between 200 to 300, right? And you're just gonna roll with it. So here she's tried 2 N10s, and like 12s, and then 4 N12s, stuff like that, and then check the spacings and stuff like that. Yep. Okay. And yep. And then you plug it into this formula for the stirrup capacity, which we saw earlier from the derivation thing. And we actually have all of these things now, right? And we just check that it passes this, and it should. And then once it passes that, we do spacing checks, max spacing, web crushing checks, and then minimum stirrup checks. It just needs to be greater than some mandatory value. Right? Okay, that's the end of it.